In this lesson, we're going to talk about improper integrals and the convergence or divergence of improper integrals. So, an improper integral occurs when you have an integral where one of the limits, either the lower limit or the upper limit, is infinity. So, if you have a function that's continuous on some interval from a to infinity, then the integral from a to infinity of that function is the limit as t approaches infinity from the integral from a to t of f of x dx. T is just standing in sort of as a dummy variable there. It could be any variable. And if f of x is continuous from negative infinity to a, then the integral from negative infinity to a of f of x dx is the limit as t approaches negative infinity of the integral from t to a of f of x dx. If the limit, if the limit exists. Okay, let's do a few examples. Okay, in our first example, we're going to determine if the interval converges or diverges, and if it does converge, we're going to find its value. So we're looking at the integral from 2 to infinity of 1 over x minus 1 squared. All right, so 1 over x minus 1 squared is inverse square variation with a transformation, a shift 1 unit to the right. So instead of having an asymptote where x is 0, we're going to have an asymptote where x is 1. Okay, I'll put that there. And then we'll draw in the curve here. So this is x is 1. And our curve is going to look like that. And we're looking to integrate from 2 to infinity. So we're looking for this bounded region here. Oh, let's make that a little bit prettier there. Okay, so in here, all of this region. And we can see that, in fact, the graph is continuous from 2 to infinity. So if the graph is continuous, then we can say that this is going to equal the limit as t approaches infinity of the integral from 2 to t of 1 over x minus 1 squared dx. Okay, so let's integrate this. We have a u to the negative 2 du, and u to the negative 2 integrates to the limit as t approaches infinity, negative u to the negative 1 from 2 to t. Let's rewrite that. This is going to be the limit as t approaches infinity of negative 1 over x minus 1 from 2 to t, which is the limit as t approaches infinity of negative 1 over t minus 1 minus negative 1 over 2 minus 1. So we have the limit as t approaches infinity of negative 1 over t minus 1 plus 1. So that is going to be negative 1 over infinity plus 1, or 0 plus 1, or 0. Oh, whoops, not 0. 0 plus 1 is actually 1. So we're saying that this area bounded by this continuous curve from 2 to infinity adds up to 1. That's pretty amazing because you think it goes on forever, but it actually has a finite sum. This interval converges. Okay, in our second example, we are going to assign an area to the region below the graph of y equals e to the x, above y equals 0, which is the x-axis, right? And to the left of x equals 1. Okay, so let's draw a graph. Okay. There are our axes. Okay. So I need a graph of x equals 1. We'll put that there. And then I need the graph of y equals e to the x. This is x equals 1. This is y equals e to the x. And this is the point 0, 1. This would be the point 1e. Okay. And we want to, it says, assign an area to the region to the left of x equals 1 and above y equals 0. So we are looking at that bounded region. And we know that area under the curve is the integral from the left bound to the right bound of the function. Now, because of what we just talked about, we can see this graph is continuous from negative infinity to 1. So I can rewrite this properly as the limit as t approaches negative infinity of the integral from t to 1 of e to the x dx. And that's going to integrate to the limit as t approaches infinity. E to the x integrates to e to the x from t to 1, which is the limit as t approaches infinity of e minus e to the t. Okay? So let's evaluate our limit. So we're going to have e minus e to the negative infinity, or e minus 1 over e to the infinity. Well, e to the infinity is just infinity, and 1 divided by infinity is 0. So we have that the area of this bounded region, the region bounded by y equals e to the x-axis, and x equals 1, that area adds up to e. Okay, let's do one more. Okay, let's do one more example. So for this example, we are going to evaluate the integral from negative infinity to infinity of 1 over 1 plus x squared dx. Okay, so what does this graph look like? This is a rational function. And if we try and draw a graph of this rational function, we can see that when x is 0, y is 1. And so that is going to be the point 0, 1. And then as the absolute value of x increases, as x goes from 0 to positive infinity or 0 to negative infinity, well, first of all, this is an even function. I'm going to have symmetry because whether I plug in x or negative x, I'm going to get the same answer. But then you can also see that as x increases, y very quickly approaches 0. So when x is 1, I'm going to get a half. When x is 2, I'm going to get a fifth. When x is 10, I'm going to get 1 over 101. So we very quickly approach 0, and the graph looks something like this, like a bell curve. Okay, you can see the graph is continuous from negative infinity to infinity. So I'm going to rewrite this as the limit as t approaches infinity. My lower limit is going to be negative t, which is negative infinity, and my upper limit is going to be t. And then I have dx over 1 plus x squared. And hopefully you remember that that integrates to inverse tangent, the angle whose tangent is x from negative t to t. Oops. 2t. What's going on there? Okay, so that's going to be the limit as t approaches infinity of the angle whose tangent is t minus the angle whose tangent is negative t. Or the angle whose tangent is infinity minus the angle whose tangent is negative infinity. So now you need to think about the inverse tangent graph. So let's quickly sketch that. Inverse tangent looks like this. We have asymptotes here and here. And then this is at pi over 2, and this is at negative pi over 2. And then the graph looks like this. Okay, so what is happening in our in our graph as x approaches infinity? Well, as x approaches infinity, y is approaching pi over 2. And as x approaches negative infinity, y is approaching negative pi over 2. And so we get that our interval converges to pi. The area bounded by 1 over 1 plus x squared, and the x-axis is exactly pi units. All right, and that is improper integrals.